Hey, today we're going to get on to, I think this is day number, oh boy, it says 5 there, but I think it's it's day 7, so it should say day 7. We're going to talk about solving equations in a complex field. Do a little bit more with roots, and I think I'm going to address what's called the Argand diagram. Argand diagram. It's a graph in Cartesian coordinates of the roots of a complex number. So let's get started. Alright, so when you're solving in the complex field, just because it's on the complex field doesn't mean that there have to be imaginary solutions. So for example, this first one here, basically I'm going to factor this, and this is going to tell me here that there's going to be potentially 4 real solutions. Okay. The other possibility is that there's 2 imaginary and 2 real, or 4 imaginary. So imaginary solutions always come in pairs. Okay, so here I could have 1 real solution and 2 imaginary solutions, or all real solutions. Right, so let's go ahead and do a little factoring here. Okay, so in this case that would be factored. And now from here, what I would probably do is set each of these equal to 0. This would yield that x squared equals 2/3. This would yield that x squared equals 2. Therefore, it looks like I'm going to get 4 real solutions. It looks like x is going to equal plus or minus the square root of 2/3. And also plus or minus the square root of 2. Alright, so we get 4 real solutions. Okay, you'll always get 4 solutions, but it depends on whether or not they're real or imaginary. Okay, let's look at this one. This one's a little bit tricky, but there's a kind of a special step here called factor by grouping. So I'm going to take these first 2 terms here and these last 2 terms here, and you might see something pretty similar in them. If I take a z squared out of the first 2, I get 2z minus 1. And I'm going to put a 2z minus 1 with a 1 in front of it. If I factor now out of both of those a 2z minus 1, and I pull that 2z minus 1 out, I'm left with z squared plus 1. Okay, now here we go. Now we're going to get a complex root, okay, or solution. Here this clearly will yield that z will equal 1/2. There's a real solution. This is where it gets interesting. Z squared equals then -1, and so z equals, this would be plus or minus the square root of -1, which means z would equal plus or minus I. Therefore, we've got 3 solutions. Z equals 1/2. There's our real solution. And z equals plus or minus I. There are 2 imaginary solutions. There you have it. We found the 3 solutions to this, looks like cubic. Yeah, that's a cubic. 1 real solution and 2 imaginaries. Let's keep moving. Okay, so in this case I've got a cubic. I can't use factor by grouping. I'm given this hint that z minus 1 minus 2i is a factor. Okay, so the first thing you need to know is what we've got written here, the complex root, or conjugate root theorem, which is just this. If z minus 1 minus 2i is a factor, then z minus 1 plus 2i is another factor. And the conjugate part of that is this plus in between. Right, so those two are conjugates for that reason, because of this minus and this plus. Alright, so what does this mean? Okay, so those are two factors. So this polynomial, 2z cubed minus 3z squared plus 8z plus 5, okay, can be represented by taking these two factors and a third factor. So z, I'm going to go minus 1 minus 2i times z minus 1 plus 2i. Okay, so right now these two z's multiplied together will give me a z squared. I want a z cubed. Therefore, I need z at the end plus something. I don't know what that something is yet. But that would be our factors of this trinomial. So let's go ahead and let's give this a shot here. Here we go. Okay, so what do I need to do? I need to FOIL these first two terms right here. And it's not as bad as it looks. Okay, so z times z is z squared. Okay, then I got z times this term here. So that would be minus z times 1 plus 2i. Then I got z times this term here, so that's minus z times 1 minus 2i. And then I've got a negative times a negative, which will be a positive 1 minus 2i times a 1 plus 2i. Okay, so let's clean this thing up here. This will be z squared minus z, distribute this to both of these terms, minus 2iz. Okay, now moving on, so minus z again, and minus, plus 2iz. And then I FOIL this over here. Now they're conjugates, so I don't really have to FOIL. I'm just going to take 1 minus 4i squared. Okay, so let's clean some things up here. I got a minus 2iz and I got a plus 2iz. Those are gone. See ya. I got a z squared minus, looks like 2z. And this right here evaluates to 5. Okay, so let's back it up a second. 2z cubed minus 3z squared plus 8z plus 5 is equal to z squared minus 2z plus 5 times something. That something would have to be a z. And in order for us to get 5, it would be 5 times 1. So this is factored form of that trinomial. Okay, but we needed a root, and we needed to know it. Therefore, we could find, in this case, we knew the first root, which gave us the second root because of the complex conjugate theorem. And now we've got factored form right here. And we know the three solutions. The three solutions to this would be z equals, would that be 1 plus 2i, 1 minus 2i, and negative 1. Negative 1 being the solution right there. Alright, there you go. That's a use of the complex conjugate theorem. Let's move on to graphing an Argand diagram. Okay, I made a mistake on the slide. I want this to be a negative 8 right here. So it's negative 8 minus 8 root 3i. So where would that exist? It exists in quadrant 3. So negative 8 minus 8 root 3i. A triangle would look like that. Oh my gosh, not well done, but that's all right. All right, so this angle right here is negative 2 pi over 3. That's going to be our argument. And our modulus, which is this right here, would then be 16. Okay, so then that means that z to the 4th equals 16 cis negative 2 pi over 3. I'm going to add on that 2 pi k, giving common denominators to make it easy there. And now I'm going to come up with those 4 roots. So if I took both sides to the 1/4 power, that would cancel. To the 1/4 power over there, I would get the 4th root of 16, which is 2, cis, and then I'm going to distribute. That would be that plus 6 pi k over 12 as well. So our first root would be 2 cis, k is 0. Okay, so if k equals 0, then I get, what would that be, negative pi over 6. And I guess I'll write it using the common denominator for now. Okay, so negative 2 pi over 12. We'll clean that up in a minute. Okay, now each time I increase k, I'm adding, looks like 6 pi k over 12. Okay, so then I would get 2 cis. If I add 6 to that, I'd get 4 pi over 12. I add it again. I get 2 cis 10 pi over 12. And I added a 4th time, or a 3rd time, I get 2 cis 16 pi over 12. Well, let's clean that up for obvious reasons. So this would be, z sub 0 would be 2 cis negative pi over 6. Z sub 1 is 2 cis pi over 3. Z sub 2 is 2 cis 5 pi over 6. And z sub 3 is, it comes right back to where we were, negative 2 pi over 3. Okay, so 16 pi over 12 is 4 pi over 3. But I'm going to write it in this form because, as we know, our answers for these arguments have to be between negative pi and pi. So that's going to work for us. Okay, so one more step here. We want to write these in Cartesian form. Right now they're in polar form. I want them in Cartesian form. So 2 cis negative pi over 6 would be the same as z sub 0 being root 3 minus I. Z sub 1 would equal 1 plus I root 3. Z sub 2 would equal negative root 3 plus I, and z sub 3 would equal negative 1 minus I root 3. Okay, so you can see some cyclic nature in that. Okay, so an Argand diagram, as you can see here, is a sketch of those roots. And you'll notice that on an Argand diagram, I have eyes and I have no eyes, right? So I've got an imaginary axis and I've got a real axis. So that means an Argand diagram requires us to have this in this Cartesian form. Okay, so z sub 0 would be at √3 negative I, which would be right about there. Okay, that's z sub 0, right? If I were to sketch this, that angle would be, what is it, negative pi over 6. Okay, then z sub 1 is 1 √3i. So there's z sub 1. Okay, then z sub 2 would be right about here. There's no coincidence that there's symmetry here. No coincidence at all. And then we get z sub 3 right here. Cool thing about this, if I would have sketched it accurately, this right here would be a square. Cool. Alright, that'd be it for today, day number 7, on solving equations on the complex plane and the Argand diagram. This right here. Argand diagram. Alright, have a good one.